4, right, when you heat a conductor, its resistance increases. Now, the learning outcomes simply says describe. It doesn't ask you to explain. So we have given you a bit of background knowledge about why that happens, but that's not what you actually need to memorise. Right? Sometimes memorising is easier if you understand why it's happening though, but that's all you need to memorise. Now, number 5 then, but is looking at a thermistor. So when you heat a thermistor, which is made of semiconductor materials, it acts in a different way. Its resistance decreases. Okay, and we've already given you the circuit symbol for a thermistor. And the last one we're defining at this section is an LDR. So when you apply more light to a light-dependent resistor, right, or LDR, its resistance decreases.
Is that number 6?
No, it's actually number 5, says both thermistors and LDRs together. Number 6. Okay, so for resistors in series, very simple. The total resistance is what you get when you add them up. Okay, I don't think I really need to give you a worked example on that. I think you'll be able to sort that one for yourself. And for resistors in parallel, and these formulas incidentally are given in the formula sheet. Now in the experiment you did it with 2 resistors, but I'll give you an example with 3 resistors. Okay, and it's probably the most awkward formula actually in NAT 5. Just takes a wee bit of getting used to though, okay? You'll be able to get used to it. So example. Calculate the total resistance, or combined, it doesn't really matter which word you use, sorry. Total resistance right, when we've got 3 resistors connected in parallel. So we just start listing what the question tells us. And it doesn't matter which one you label 1, 2 and 3, you'll get the same answer at the end. And you're being asked the total or combined resistance. Okay, so we're identifying it's parallel, so it's the second formula that we select from up the top here. Actually, if you want to highlight the formulas, put them in a box or something like that. That's what we usually do with new formulas, isn't it? And for our substitution, we don't know RT, so we'll leave that as it is. Okay, so show your working, show your substitution of R1, R2 and R3. But then you can now do this in your calculator.
Would you ever be asked to do it, like, find out?
Your calculator, right, we'll probably write that 1 over RT equals 7 over 12. But then you've got to remember, and this is a bit where people make a lot of careless mistakes, they kind of stop there and think, well, the answer's 7 over 12. Your final step has got to be flipping both sides. So if RT over 1, right, if 1 over RT is 7 over 12, then RT over 1 is 12 over 7, i.e. RT, and you can get your calculator out, is 1.71 ohms. Okay, so worked example. We'll start with a fairly basic one. So we've got a circuit. Right, with a battery and a couple of resistors. Shh. Now I'm going to label these resistors R1 and R2. It doesn't matter which way round you put them. It doesn't affect. Okay, so if imagine using a 6-volt battery. Okay. So the information we're given. We're given the supply voltage. R1 and R2. So it's quite straightforward to get the information out of this question. While we're listing the information, remember to do any unit conversions, right? So any prefixes. So here we've got kilo ohms. Convert them at that point, get everything into standard units. Now, labelling in circuits is actually quite important because now in these circuits, we can't just talk about the voltage. We could talk about the supply voltage, we could talk about voltage 1, voltage 2, etc. So it is important, right, how you label. So which current am I being asked? Well, underlying that is a circuit rule that you should know the current is the same everywhere in a series circuit. So because it's a supply voltage, I know I'm going to put IS equals question mark, supply current. But that's equal to I1 and equal to I2. Now what formula links IS, right, VS, R1 and R2? Well, there isn't a single formula which links all of them together. That's what's the key idea about these worked examples. But what we do have is V equals IR. And we've got the fact that in a series circuit, the total resistance, which I'm going to call RS, is R1 plus R2. Okay, so by putting both of those ideas together, then we can work out the current. So the first formula we're going to use is RS equals R1 plus R2. And quite often people don't even show the working for this, but obviously it is important, just in case you make a wee slip, that a marker knows where the numbers are coming from. So adding those two together, we can get RS is 3000 ohms. And then once we've got that, we can do V. So basically V equals IR with everything having a subscript S. You can do the same V1 equals I1 times R1, V2 equals I2 times R2. But the kind of underlying idea there is that you can apply Ohm's law to a whole circuit. You can apply it to any bit within the circuit as well. So now I can do some fairly straightforward substitution. And then quick arithmetic. Just swap sides to start. Divide both sides by 3000 to get IS on its own. And there we get a final answer.